50 minutes for coffee break. And then we come back 11:30 sharp.
To two high-rise buildings, one in Qatar and the other one in Korea. This is a diagram produced by the Council for Tall Buildings and the Urban Habitat, showing how the rate of increase in high-rise buildings in excess of 150 metres tall has accelerated. And you see, prior to the 1970s, we had very few high-rise buildings, and yet in the decade, in the 2000 decade, we had hundreds and hundreds of these buildings. And I would imagine that the current statistic, even with the global financial crisis, will see the next decade accelerate again in the construction of tall buildings. So we have an ongoing challenge here to design foundations which are safe and economical. We need to understand some of the characteristics of tall buildings. The loads are very high, and as you get higher, the loads actually increase more rapidly than the height. So it's a non-linear increase in height. We have often low-rise areas adjacent to our tower. This is podiums with shopping centres. And so they're much more lightly loaded than the towers themselves, and so we have the potential for differential settlements. We have high lateral forces and moments from wind, and so this creates quite a problem. We have cyclic loading, again, due to the wind, and so we need to take that into account. We may have dynamic issues related to our foundations, and we need to design for seismic loadings due to both inertial loading and kinematic loading. That's the movement of the ground and its interaction on the structures. We have a number of other issues in terms of dynamics and so on. So there are significant number of issues related to tall buildings. If we're going to design foundations economically, there are a number of things that we need to do. Firstly, we need to have the right type of foundation. So we have to have an appropriate foundation concept. We have to use an appropriate design method and design criteria. We need, and this is critical of course, to have appropriate ground data and design parameters. And this is often one of the most critical aspects of foundation design, is getting the parameters. We need to have quality construction. We need to have appropriate foundation element testing. In particular, if we're dealing with deep foundations, we need to do pile load testing, and we should always have during and after construction performance monitoring so that we understand how well our structure is performing in relation to our design expectations. I think many of you would know that generally when we're dealing with buildings of any size, we have at least three options for foundation systems. We can use a raft if the building isn't exceedingly tall and the ground conditions are very good. We can use a fully piled system so that all the loads are designed to be carried by the piles. Or we can use a combination of these, a pile draft system, and that in many cases is likely to be the most economical and effective option for many sites. And indeed, the two cases I'll show you are both pile draft foundations. Geotechnical reduction factors that we apply to our estimated ultimate capacity vertically and laterally, and we do an analysis to try and ensure that under these load combinations, the weakened foundation system, that is the foundation system that has factored down capacities, will not collapse. And if that condition is satisfied, then we basically say the building will stand up. And so that's the requirement, that under these ultimate limit state loads, no collapse will occur. In terms of serviceability, fairly straightforward. This is what we've always done. We apply the serviceability load combinations. So these are, of course, generally less than the ultimate limit state. They're like dead load plus some proportion of live load normally. And we use our best estimates of soil resistance and soil stiffness. We don't try and factor the stiffness or resistance of the ground in this type of calculation. In terms of structural design, we actually have to do a separate calculation because it is not correct to factor down your pile capacities when you're doing a structural design analysis. The reason is that if we factor down our capacities, then we're limiting the amount of axial load that can come onto the pile, and so we may under-predict the amount of vertical load that the pile has to be designed for. So what we do now is that we use our unfactored soil resistances in this analysis, and we calculate the loads and moments, and then we apply a factor onto those calculated moments and loads. Importantly, and this is really critical, we don't work in isolation. We work in conjunction with the structural engineers. And it's important that we recognise that we're dealing with an interactive system. What we typically do when we've gone through our analysis is that we will provide for the structural engineer values of the stiffness of each of the piles in the foundation system, which they then put into their structural analysis to work out what needs to be done from the point of view of the structure. And I think if that's done in the right way, then you get a very good outcome. One of the things that I emphasise here is that when we provide stiffness values to our structural colleagues, they must account for the interaction among the piles in the group. You can't just take a load test result from a single isolated pile and apply that to a large group of piles, because you will get a result that is far too stiff. And I'll show you an example of this in a moment. In terms of the analyses that we need to do, what are the desirable things? Well, we need to be able to have an analysis which looks at pile groups subjected to vertical loads and horizontal loads and moments. We need to be able to handle realistic soil profiles. We need to be able to incorporate nonlinear soil pile behaviour. We need ideally to be able to handle different pile types within a group, because in modern design we don't have to use the same length diameter of pile as perhaps we've done in the past. We can be more sophisticated than that. We need to be able to incorporate the stiffness of the raft and the stiffness of the structure. So all of these things are desirable. There's a number of programs that are around that we use or can use. These three are commercially available. This is a program I developed over 30 years ago, so it's an old one. This is Professor Randolph's Piglet program. This is an updated version, Repute, which is now commercially available in the UK. All of these are pile group analysis programs. They all have similar abilities, give or take. We use these as a routine design tool when we're trying to come up with the optimum foundation system. What we then do is that we'll use one of these more sophisticated tools like Plaxis 2 and 3D or Abacus or the FLAC 2 and 3D, and there are of course other 2 and 3-dimensional programs. We will use those programs in the final stages of design to make sure that the system that we've come up with performs as we think it will according to these more simple programs. In our company, we have a number of other programs, and I'll just mention these very quickly because I'll show you one or two results. But these are programs that we've developed internally to do pile groups, two of these, and one that deals with the settlement analysis of pile graphs. I should say that there is no single program that is not a finite element program that can provide everything we would like to have. There are always limitations on any of these programs. And if you really want the ultimate in versatility, then you have to go to the prolonged process of a three-dimensional finite element analysis. In the written paper, I've just shown an example, a very simple example, before we get on to reality, of a square raft with 9 or 15 piles. And what I've done there is I've just run through analyses to check the 9 and 15 pile raft solutions to that problem. And without going into detail, we find here that for both of those foundations, the ultimate limit state condition is satisfied. This is when we reduce the pile capacities and we put on all the loads, it stays up. However, the one thing that is not satisfied with the 9 pile group is the cyclic load criterion. We find that with the cyclic wind loads that we've specified in this problem, that the cyclic axial load exceeds half the ultimate skin friction. Serviceability is fine, the settlements are not that different. We have relatively small differences in the other characteristics of behaviour. So in this particular case, everything is fine for the 9 pile group except for the amount of cyclic loading that it would have to resist. Now, just before I go on to real examples, just to point out that there are, in fact, if we're dealing with pile draft systems, there are 4 sets of interactions which any good analysis should consider. There's the interaction between one part of the raft and another. There's the interaction between one pile and another. There's the interaction between a pile and a raft, and the interaction between the raft and the pile. So there are 4 interactions that we need to consider in a complete analysis. For the case, the simple case I showed you previously, this little diagram just shows the axial stiffness of the foundation that we calculate for 3 cases. The first one is where we take into account all the interactions. The second is where we consider only the interaction between the piles. And the third is where we ignore all the interactions. This is for the 9 piles, this is for the 15 piles. And without going into too much detail, if you ignore all the interactions, you will get a stiffness that is 3 to 4 times higher than the real value. In other words, you will underpredict the settlements by a factor of 3 or 4 if you ignore the interactions. So it's absolutely critical in foundation design for tall buildings that you take account of these interactions. The other thing that, of course, we have to do, and I don't have time to go into detail, is we need to make assessments of the key parameters. The ultimate shaft friction, the ultimate end bearing, the soil stiffness for vertical loading, both for long-term, if we're dealing with long-term settlements, and also for short-term loading, because we might be concerned about the movement of the foundation under wind or seismic loading. We need to look at ultimate lateral pressures to see whether there's any lateral problems, and the stiffness that we use under lateral loading may well be different from that under vertical loading. And if we're dealing with dynamic loadings, then we need to address the issue of dynamic parameters. Another absolutely critical issue, and one that I think is almost universally adopted now, with tall buildings is that we need to be able to do pile load tests to test our design and to make sure that everything is as we expect. And in many cases, we've found that our design assumptions are conservative, so we can in fact either reduce the number or size of the piles. And I've just indicated here that the Osterberg cell test, which I think some of you may be familiar with, is turning out to be a very effective form of testing. It has actually been used here in Vietnam. It was used for the Mekong River Bridge down near Ho Chi Minh City some years ago, and it's a very convenient form of test. Now, to the first of the two cases I want to consider, and quite briefly, time is not going to permit me to say too much about these, but this is a 435-metre building in Doha in Qatar, and this is what hopefully it will look like one of these days. The foundation layout is shown here. There's very heavy loadings in the middle here. And the ground profile is rather interesting because unlike many other profiles, you get the good ground conditions up here and the poor ground conditions down here. And we have a very poor limestone or chalk deposit that extends from about 40 or 50 metres below the ground surface down to about 120 metres. So if you want end-bearing piles, you're out of luck unless you're prepared to have 120-metre long piles, which we weren't in this particular case. So this is a situation where clearly we make use of this good limestone, the Simsima limestone near the surface. We put the raft on that and then we add to that piles to increase the capacity and the stiffness of the system. These are the foundation loads. I won't spend too much time on those, but they're quite significant loads, vertical loads in excess of 3,000 meganewtons and quite large lateral loads and moments. The foundation system consisted of 232 piles, 1.5 metres diameter, and only up to 32 metres long, so they weren't particularly long. This is below the base of the raft. The raft itself was not very thick, these days 2.5 metre thick, but it was founded in that better upper layer. And as I said, the properties of the rust chalk, the bad layer, do not really improve with depth. These are the outcomes of our overall stability analysis, and when we do these stability analyses, and we do it with our program called CLAP, we have a whole series of load combinations which we examine. We apply reduction factors to our estimated axial and lateral capacities, and we see if the system is stable or not. And for all of these the 8 load combinations, it was stable. The settlements that we calculate are not very meaningful because they're all non-linear, but it showed that that foundation system was stable. This is the check for cyclic loading. These, on the horizontal axis, we have each of the 220 odd piles, 232 piles, with the cyclic load component as a proportion of the ultimate shaft friction. Now we try and keep that proportion to 1/2, and we just managed to make it here with some of the extreme piles. So this system then satisfied our cyclic loading criterion. We then went through a settlement analysis using our internal program called GARP, Geotechnical Analysis of Raft with Piles, and this is the sort of thing that we get out of this, just contours of settlement. Maximum settlement's quite large, and well in excess of 100 millimetres here, tending towards 200 in the long term. And with that program we can also get settlement profiles, so we can look at any particular section and see how the profile is going. And this is where the building is at the moment. I was in Doha 3 or 4 months ago, and it's been another victim, perhaps temporarily, of the financial crisis. It's only gone up to about 10 or 12 stories, and it's sitting there. But the foundations are in, so that's good. The next case I want to describe is a building that is currently under construction, although again it's halted because of financial issues. It's the 600-metre tall Incheon 151 tower, so it's supposed to have 151 stories. Quite a dramatic looking bit of architecture, located not very far away from Incheon Airport in South Korea. And it's actually, the other thing that's exciting is it's on a reclaimed area of land. So this is what it was like before the reclamation took place. Another challenge is that the geological conditions here are quite complex. There is actually an old fault that runs across here, or certainly a sheared area. And so we have here a site where you cannot have a single geotechnical model for the whole site because of the differences in the geology. So we have actually split this site up into 8 sectors and had a different geotechnical model for each of those 8 sectors. The model itself, a little more straightforward now. We have marine deposits, then some weathered soil and weathered or very weak rock, and then there's a deposit that's called soft rock. It's not necessarily that soft, but what's happening is that the foundations are actually going into this weaker rock layer, which typically has unconfined compressive strengths of the order of 4 to 10 megapascals. And this is some of the typical core. It doesn't actually look all that great, but the material into which the piles are founded is better than this. The foundation system, again, is a pile draft, 172 piles, larger diameter, 2.5 metres, and the piles are being founded into that soft rock with a raft thickness now significant of 5.5 metres. And this is the foundation layout, just a central part with 4 legs basically splaying out. The results of the ultimate limit state analysis, we applied reduction factors of 0.64 for the lateral capacity, and that low reduction factor for lateral represents the fact that there's a greater degree of uncertainty because of the soft marine clays than there is with the stiffer deposits lower down. But basically, that foundation system was found to be stable for the ultimate limit state. The cyclic load check again came out okay. This is the ratio of the cyclic load to the ultimate shaft resistance for each of the 172 piles, and they were all below the 0.5 limit. And these are the settlement contours, showing also not only the tower but the outside area where there will be a podium. Maximum settlements of the order of 90 to 100 millimetres. And as part of the output of that program, we can also get the distribution of loads in the piles, and therefore we can get the axial stiffness and the lateral stiffness of each of the piles in the foundation system. That project is currently on hold again. There's been pile load testing carried out, which indicated that our design values for shaft friction in the better materials were quite conservative, and so if construction does continue, then it's likely that we will be able to trim the size of the piles somewhat. I just wanted to very quickly show you some of the other buildings that are on pile drafts. There's this rather interesting building, 220 metres tall in Doha. This is the iconic hotel, the Burj Al Arab in Dubai, and this is on a pile draft. I was fortunate enough to be involved in assisting W.S. Atkins in the design of that. And there's a very interesting paper that will be presented tomorrow by our conference technical leader, Dr. Fung, dealing with the International Commerce Center in Kowloon in Hong Kong, 480 plus meters tall. And just to show that we don't only restrict ourselves to piles, this is a raft plus barrettes rather than raft plus piles. Large number of piles, and Dr. Fung has done a very nice complex analysis to look at the overall behaviour. And this is the sort of thing, as I said before, that you can do once the design has been established by more reasonable methods. You can then check that everything is performing as you would hope. The Burj Dubai, now the Burj Khalifa, is on a pile draft system, currently the world's tallest at 828 meters, and we assisted Haida Consulting in the design of that. We were the geotechnical peer reviewers. Measurements of the settlements of this foundation have been made, and as of a couple of years ago, and these are the latest ones I can get out of the people involved.
Professor Poulos for very exciting lecture, and I think that is very useful for engineers in Vietnam, both the geotechnical and structural engineer, because both the number and the height of high-rise in Vietnam increased very, very considerably during the last decade. Thank you very much. And please, Mr. Huang.
Ladies and gentlemen, so this morning is finished here, so it's time for lunch. Maybe you are waiting for that, many of you. So we have 1 hour from 12:15 to 13:15. The dining hall is on the 4th floor. You can use the elevator on your left.